Hello everyone, myself Ajita. I'm a postgraduate scholar doing my masters in power electronics in Beltech Dr. RR and Dr. SR Technical University. First of all, I thank everyone listening to this video. Thank you so much. I am here to present my final year project comparison of dynamic performance improvement of wind farm with a Doubly Fed Induction Generator and Permanent Magnet Synchronous Generator using STATCOM. And this project is guided by Dr. P. Chandrasekhar. He is a professor and head of Department of Electrical and Electronics Engineering in the same reputed university. So we know that everything in this today's world depends on electric power, electricity. And this electric power generation in the near future is going to be rely on renewable and eco-friendly energy resources such as wind, solar, hydropower, geothermal, hydrogen, biomass, etc. due to the existence of your fossil fuel coal. So, among these renewable energy resources, wind is the most available resource in our country, and it is considered to be the cheapest and one of the major renewable resources. This is because we have three passes in our country, and now many of the scientists are working on how to get maximum and efficient performance from this wind farm. I will show that installed wind power capacity in our country. Now you can see here we have 21,923 megawatt of wind power installed capacity in our country. Among this, 35% of them are generated from Tamil Nadu. In Tamil Nadu, we have separate agency for this called Tamil Nadu Energy Development Agency (TNEDA). So we can call that Tamil Nadu is mother of wind power generation in our country. So uh, in this project, the dynamic performance improvement of wind farm with permanent magnet synchronous generator and doubly fed induction generator using STATCOM are to be analyzed. That is, we know we generate a power and we transmit it to a transmission line to the load centers or a distributors or to direct consumers. So when we transmit a power, we know the system may be subjected to many faults or disturbances due to various factors. So in such cases, we know in a wind farm, number of generators will be running in parallel, and we will take a point of common coupling called PCC, and then from there we will supply it to the load centers. So what we have suggested is we have suggested in this project is due to the fault occurs, your system stability is disturbed. It means it will affect your power generator and many things. So in such cases, if we inject a FAC devices or a compensating devices so that it will provide you a reactive power support or voltage support required by your system, so that your system will be recovered from the fault and you can get the effective output, and thus we can improve the transient performance of your wind farm with STATCOM. So this project gives basic idea about the performance of static synchronous compensator in your wind farm. So why this project? Yeah, why I have selected this one? In India we have most of the wind farms employed with fixed wind turbines and induction generator. But the limitations of such generators are low efficiency and poor power quality. So we know in some cases we know the wind blow is not constant, and in some cases we have very high wind speed but the demand is very low, and sometimes we have very low wind speed and the demand is very huge. So what we all want is we need a generator that can be operate in variable speed mode, and it can generate a required power so that it can generate a required power. So these are the factors which gives ways to the variable speed wind turbine generators such as doubly fed induction generator and permanent magnet synchronous generator. So there is a debate going on in wind power industry among these two or between these two, which is the best. Many are promoting the use of doubly fed induction generator, and while some expressing doubt over the advantages of permanent magnet synchronous generator. So now let's see about these two generators in detail in the further slides. And all I want to say is this project is a small step forward. The benefits of STATCOM wind farm integration based on DFIG and PMSG, and which generator along with the STATCOM will give you better dynamic performance. So let's see about permanent magnet synchronous generator. You know that permanent magnet synchronous generator, in this your DC excitation is provided by the permanent magnet itself instead of the field coil. Thus it eliminates the use of slip ring brushes and field coils. Because of this, the overall electrical losses will be reduced. And also, as I told, it can operate on variable speed mode. That makes it better solution. And also it has very high efficiency, low maintenance, because you know the nacelle mostly consists of wind turbine and a shaft and a gearbox and again a shaft and then generator. This is what your nacelle is made up of. In case of PMSG, the need of gearboxes avoided, so we don't use gearbox in this. So this will reduce the weight of your gearbox and thus therefore the reduction of the cost. And we know that when the wind speed changes, the rotor speed also changes. Therefore, the frequency of the induced voltage also changes. But we know the grid has a fixed constant frequency. So in such cases, the use of ordinary induction generator is not much worthy. So in case of PMSG, we know it is connected to the grid through a converter. So the converter will adapt the frequency of the induced voltage to the grid frequency. So there is no frequency problems when we use PMSG along with converters. And the most disadvantage of this PMSG is cost of your permanent magnet, that is your rare earth metals. This rare earth metals is costly, but we have to understand that it is just a capital or initial cost. When we consider the overall system performance, as I told before, there is no gearbox, so it will reduce the weight as well as the cost as well as your maintenance. So overall, when we consider the overall system performance, this PMSG is economical. And another disadvantage is, when the wind speed is low, we can still generate power by using by increasing the number of folds of your PMSG. That is another advantages. Now let's see about doubly fed induction generator. From the diagram, you can see that here the stator is connected to the grid directly and your rotor is connected to the grid through the frequency converter. So the basic idea of your DFIG is to interpose a frequency converter between the variable frequency induction generator and the fixed frequency grid. So hence the name, it is called Doubly Fed Induction Generator. Now let's see about the wind turbine model used in this simulation. This wind turbine model, you can see here, it has three inputs: your wind speed, generator speed and the pitch angle. Wind speed is nothing. It may vary from 3 meter per second to 25 meter per second. But in general, or in this practical, in this simulation purpose, we have used a constant 12 meter per second wind speed, and the generator speed is nothing, it's just a feedback signal from the generator. And the pitch angle, here we have used 0 degree pitch angle, because we know when the pitch angle is 0, we will get the maximum performance coefficient. When the performance coefficient is maximum, you will get the maximum power output. And let me tell you the formula of the power of your turbine, output power of your turbine. It is nothing but of rho Cp function of lambda A wind speed power cube. Here rho is the air density, Cp is the performance coefficient, power coefficient, A is the rotor turbine area, and Vw is the wind speed. Now let's see here how we are getting this power PM. As I told before, lambda is nothing but tip speed ratio. It is nothing but ratio of the rotor generator tip speed to the wind speed. So here we get the value of lambda by generator speed divided by the wind speed will give a lambda value. So Cp is a function of lambda and beta. This will give the value of Cp, and here we have wind speed power Q. So product of these will give you power, output power. So this will give you an output torque. From this we can get the motor shaft torque. So this is what I have explained before, the CP value, how the CP will be maximum when the pitch angle is 0, and the 3 inputs of your wind turbine model. Okay, fine. Then we have something called two-mass drivetrain. This is nothing but a coupling system. That is, we have a turbine and a shaft and then the generator. So this will be used between your wind turbine and the generator so that it can generate a shaft torque that is needed by your generator. So in this we will consider the rotor angular speed at both the wind turbine end as well as the generator end. This two-mass drivetrain is very much suitable for your transient stability analysis. That's why it is used here in this model. And then you can see the compensating device used here. We have used a static synchronous compensator. Why means it is something that will respond quickly to your fault conditions, and it will respond very quickly, and that's why it has been used. So STATCOM is nothing. It is a shunt connected reactive power compensation device that is capable of generating and absorbing reactive power, and in which the output can be varied to control the specific parameters of an electric system. Here, the power generation, that is your reactive power generation and absorption, are entirely done by means of electronic processing of the voltage and current waveforms in a voltage source converter. This diagram will give you a good idea about your STATCOM. STATCOM, here you can see it has a voltage source converter, and it is connected to the AC bus system through the coupling transformer, or we can use a reactor also, and this is your DC source for your VSC, for your voltage source converter. So here the reactive power is exchanged between the voltage source converter and your AC bus system. Let's see how it works. To exchange this, it can be mainly done by controlling this ES. You can see here ES and ET. ES is nothing but output of this voltage source converter. It is the bus utility bus voltage. Okay. So when this ES is greater than ET, that is your output converter output voltage is greater than your bus voltage, then current will be flowing from this voltage source converter to the AC bus through this coupling transformer. In such cases, the converter will generate a capacitive reactive power. So when the other cases, when this ES is less than this ET, current will flow from AC bus system to the converter through the coupling transformer. In such cases, the converter will absorb a inductive reactive power. So what will happen when ES is equal to ET? Yeah, there will be no reactive power exchange. So in such cases, the STATCOM is said to be in floating state. So this is how the reactive power is exchanged in your STATCOM. And here the real power can also be exchanged by adjusting the phase shift between the output of your three-phase voltage source converter as well as the bus voltage. So let's see about Cascaded edge bridge 5-level inverter. Here, for what purpose I have used 5-level Cascaded inverter means, it can give you the voltage appropriate proportional voltage required by your system, and it has separate DC sources. It can be battery, solar cell, fuel cell, anything. So each cell would generate a voltage of 3 levels: plus VDC, 0 and minus VDC. And when the switches S1 and S4 are on, we will get plus VDC, and when S2 and S4 are on, we will get minus VDC. When S1 and S2 or S3 or S4 is on, the output voltage will be 0. So the output voltage of this is nothing but the sum of the voltage that is generated by each of the cell. So the advantages of this multi-level inverter is it has improved output voltage quality, smaller filter size, low EMI, that is your electromagnetic interference is very less, and also it has low harmonic distortions, which is very very important for your power quality improvement performances. Now see the Simulation models and results. Okay, as I told, here we are going to compare the simulation of both Permanent Magnet Synchronous Generator and Doubly Fed Induction Generator. First, let's see about the Permanent Magnet Synchronous Generator simulation model. Here we can see the wind power generation, the subsystem. I will show the subsystem in the next slide. What I have done, I will show that one. So here, so from this, the electric power is generated and is transmitted through the transmission line through the three-phase RL load. You can see here R and L, three-phase RL load. And I have a three-phase fault here. It can be any single line to ground fault, line to line fault, anything. Here in the simulation model I have used a three-phase fault, and this is your STATCOM with the multi-level inverter. We can also check the performance of this by just disconnecting these three lines, so that your STATCOM will be detached from your system, and we can analyze the performance without STATCOM, and by connecting it we can analyze the performance with STATCOM. So this is the simulation model, and I will now show the wind power generation. So this is the generation diagram. Here you can see the wind turbine model, 2-mass drivetrain, and the generator, your PMSG. As I told, the wind turbine model has three inputs: generated speed, pitch angle, and the wind speed, and it will generate a torque. This torque ends in the PMSG, and we can see the feedback generator speed also. From this, we can see what are the things we have calculated in the generator terminal. We have line voltage, VAV, line current, RMS voltage, RMS current, and your power output and the rotor speed. These are the parameters we have generated from this. So for the simulation model, we have used a constant wind speed and pitch angle. Constant wind speed is 12 meter per second. We can see here it's 12 meter per second, and your pitch angle is 0. This is maintained constant throughout your simulation. Okay, now see performance of PMSG without STATCOM. So as I told, the whole dynamic model is made in or established in your MATLAB simulator. It consists of wind power generation, your transmission line with a fault induced in it, and a compensating device STATCOM and a RL load. As I told, the three-phase fault is going to occur in the transmission line at a time period of 0.3 to 0.35. It can be occur at any period between, so we can use even 0.2 to 0.25, 0.1 to 0.5, anything. And we have measure the values of line voltage, line current, RMS voltage and current, power, rotor speed, and also the system output voltage and current at the point of common coupling. These are the things we have measured, and we can see the output waveform. As I told, we have introduced a fault here in 0.3 to 0.35. We can see the voltage sap, voltage dip here, and how the current is disturbed, and RMS voltage, RMS current, everything is disturbed, and you can see the changes in your power generator also. Because of this, your voltage, rotor speed is also decayed or decreased. So these are the changes when there is a fault is induced in 0.3 to 35. This is just the performance without your STATCOM. Okay, you can see the system output voltage and current. It's a big voltage sag. Current is very much disturbed. This is your uncontrolled active and reactive. You know that when a fault occurs, when there is no fault, your reactive power will be 0. When a fault occurs, this generator will give you a reactive power. Okay, so the generator, as it can operate in, this is one of the advantage of your permanent magnet synchronous generator. When a fault occurs, your generator itself can generate a reactive power support required by your system. So these figures clearly shows that when a three-phase fault is occurred, what are the changes, what are the disturbances occurred in the voltage power generators. So these can be improved, this performance can be improved by using a 5-level cascaded multi-level inverter based STATCOM in your system. To analyze this, again we have induced a fault in three-phase, same setup is made, and we just connected the STATCOM at the point of common coupling and just measured Now let's see the performance of PMSG with STATCOM. As I told before, the STATCOM will improve the performance of your system by generating or absorbing the reactive power into or from the system, and it is a rapid and continuous response characteristics which provide faster and smoother dynamic voltage control. And here we have used a cascaded edge bridge 5-level inverter based STATCOM. Okay, so let's see. Yeah, again we have induced a fault at the time period of 0.3 to 0.35 in the same transmission line, and with the help of transform it will provide voltage support to the system, and this simulation output will give the better knowledge of the dynamic behavior of the generator and the overall system performance. So this is your output. So now you can see at point 0.3 to 0.35 your voltage is compensated. I mean voltage sag is compensated, your current is compensated, so that similarly your RMS voltage, RMS current, and the power generator, and your rotor speed, everything is neutralized, and the system is stabilized, and this would give the perfect output voltages. And this is the system output voltage and current. We can see it is also compensated. It is very good. So now we know that the improvement in dynamic performance of wind farm can be achieved effectively by using the 5-level cascaded multi-level inverter based STATCOM in the system. From the figures, it is very clearly shows that performance of PMSG with the STATCOM is very good. Now we can see the Doubly Fed Induction Generator simulation model. In this, you can see it is a grid system. The grid is, and in this is your stator and rotor. The stator is connected directly to the grid, and the rotor is connected through the converters to the grid. So that's why it is called Doubly Fed Induction Generator. And in the simulation model, we have a separate voltage and separate control for grid side control, grid side converter control, as well as your rotor side converter control. That's what is here. And this is your simulation model. We have used a 3-phase fault in this, and now see how the performance is. So this is the performance of your Doubly Fed induction generator without STATCOM, and here we can see at 0.3 to 0.5 current is distorted voltage, because as I told here the DFIG can also generate the reactive power when the fault occurs, so that we know that as per QV relationship the voltage is compensated, but your distortions in current is still there, and this is the active and reactive power. As I told, when the fault occurs it is generating the reactive power. And this is the performance of DFIG with STATCOM, and your voltage, current, both are compensated, and this is your output active and reactive power. You can see how the active power is smooth, and the reactive power once fault occurs it generate, and then it goes to the normal state, that is 0. Then it's going to a normal state. And this is the DC link voltage. It is nothing but between your inverter and converter. I mean that is rotor side converter and stator side converter. DC link voltage is used, and this is your rotor speed. Everything is neutralized. So conclusion from this, what we have seen is, here an attempt has been made in this project to compare the performance of the wind energy conversion system based on Doubly Fed induction generator and permanent magnet synchronous generator. The system models are developed in the MATLAB Simulink. It has presented the detailed model of the variable speed wind turbine with DFIG and PMSG connected to the power grid. The simulations were carried out when the system is under fault, under a 3-phase fault, and how it behaves with and without STATCOM. And a comparison also is made. The simulation results shows that the wind farm with PMSG using STATCOM and also DFIG using STATCOM gives a better performance when the system is under fault. I mean the STATCOM is playing a major role in this, but considering the overall system performance, there's less oscillations in our active power. You have seen that active and reactive power waveform when the fault occurs, both the generators are generating or providing reactive power support to the system, but the time taken to settle down, that is very important. In that case, PMSG is better and it is fast and rapid, and the generator speed deviations is low in case of PMSG. So, as I told before, the time taken by the system to recover from the fault and the less maintenance due to the absence of gearbox makes this permanent magnet synchronous generator with full scale converter a reliable one. And as a whole, it can be concluded that wind energy conversion system using PMSG as wind turbine generator is best among the other wind generators in that induction generator, squirrel cage induction generator, double fed induction generators. So PMSG is the best among them, and I thank everyone who helped to make this project. So what are the references I have used is, so Panikurin PMG versus DFIG. This is my transition paper actually. From this only I got the basic idea to compare this performance of these two. These are my other references. I have used a Hingorani book as well as Muhammad book to study the performance of the STATCOM, and each and every paper gives the basic idea of to develop your wind turbine model, generator model, and why STATCOM is preferred in wind farm, and why H-bridge multi-level inverter has been used. These are the things I got it from these papers, and thanks to everyone. So conference and publications. I have already published, attended many conferences regarding this topic, and everyone appreciated my work for this one. So these are the three international conferences and two journal publications regarding this project work, and two of them are published in Scopus Journal and Initiative. So any questions? If you guys have any doubt or anything, you find any fault in my work, any corrections you have to tell me, yeah, you can just post a comment and I will respond to you. So thank you for listening. Very nice. Thank you all.